viewers, in one of my previous lectures, I had introduced the reactive methylene compounds to you. You are already familiar with the fact that these compounds are reactive due to presence of alpha acidic hydrogen. On your screens, you can see the structure of 2,4-pentane dione. In this, methylene group is sandwiched between two electron withdrawing acetyl groups. The acidic hydrogen has been indicated by a yellow colored box. So this methylene group, which is sandwiched between two electron withdrawing groups, is reactive methylene group, and the hydrogens attached to it are acidic in nature because the two acetyl groups pull the electrons from this methylene carbon by inductive effect, that is minus I effect, as a result of which there is partial positive charge on this methylene carbon, resulting in bond dissociation between the alpha carbon and the hydrogen attached to it, because the bond here has weakened. So the presence of an alpha acidic hydrogens in a molecule provides the possibility of certain chemical reactions. Therefore, it is very important for us to identify these alpha acidic hydrogens in a given molecule. On your screens, again, I have shown another structure of pentanal. In pentanal, what we find that the aldehyde group, which is the CHO group, is the functional group. And the carbon, which is shown in purple, which is directly attached to the aldehyde group, is the alpha carbon. And the hydrogens which are attached to this carbon are the alpha hydrogens. As you can see on your screens, the hydrogen which is attached to the aldehyde group, that is, which is attached directly to the carbonyl group, to the carbon of the carbonyl group, is not acidic in nature. So this is not acidic in nature, and this is not alpha hydrogen. The point to be noted here is the hydrogen of the aldehyde group is not alpha hydrogen. It is forming the part of the functional group. Whereas the hydrogens which are shown by purple and which are attached to a carbon which is again indicated by purple are acidic in nature. The carbon next to this carbon, that is on the left hand side, is the beta carbon, and next carbon is the gamma carbon. What we are interested here are the alpha hydrogens. So the hydrogens, alpha hydrogens, which are directly attached to a carbonyl group, will display unusual acidity. Now the question arises that why are these hydrogens acidic, whereas the hydrogens of the beta carbon and the gamma carbon are not acidic in nature? This is due to two factors which affect the stability of the base formed. First, the electrons left behind when the proton is removed are delocalized. And electron delocalization increases the stability of the molecule. You already know this. The second point, the electrons are also delocalized on the oxygen. And we know oxygen is more electronegative than carbon. Since oxygen is more electronegative than carbon, it is able to adjust the electrons much better. Therefore, we find that the carb anion which is being formed after the removal of alpha hydrogen is resonance stabilized. So what you find here is, as you can see on your screens, now once the proton has been removed from alpha carbon, we get a negative charge on carbon which is adjacent to the carbonyl group. Now this negative charge and the pi bond of the carbonyl group are in conjugation. Since they are in conjugation, resonance takes place. When resonance takes place, there is a double bond between carbon and carbon, and the pi electrons of the CO bond are pulled towards oxygen, since oxygen is more electronegative, as a result of which oxygen has a negative charge. So the second structure, contributing structure, is more stable. And the second point that you have to keep in mind here, that the negative charge is being delocalized over carbon, carbon and oxygen. Therefore, what do we say? That this base which is being formed as the removal of H plus from alpha carbon is stable. And hence, these hydrogens, alpha hydrogens, are acidic in nature. Why are they acidic in nature? Because an electron withdrawing carbonyl group is present there. Not only this, we find that this effect of stabilizing of base by carbonyl group is seen when we compare the pKa values for the alpha hydrogens of aldehydes, which have a pKa value between 16 and 18, that of ketones which have a pKa value of 19 to 21, and esters which have a pKa value of 23 to 25, which indicates that aldehydes, the alpha hydrogen of aldehydes, is most acidic, followed by that of ketones and esters. And point to be noted here is that the hydrogen which is attached to a typical alkyl group is not acidic in nature, because there the pKa value is between 40 to 50. So that means if a methylene group or if a group is attached to an electron withdrawing group, which may be an acetyl group, which may be an ester group, which may be a cyano group, that means the hydrogen which is attached to the carbon, which is directly attached to electron withdrawing group, will be acidic in nature. So the point again which we have to note here, that because of the acidity of alpha hydrogens, many carbonyl containing molecules undergo a proton transfer equilibrium called tautomerism. So when we talk of tautomerism, what is tautomerism? You have to remember, tautomerism is a special type of functional isomerism in which there is dynamic equilibrium between the two forms. So let us see what happens in an acidic condition. So if we are talking of a keto-tautomerism, tautomer, what we find that in this case, an acid-base reaction takes place in which the lone pair of electrons on the oxygen acts as a base and it picks up a proton from the medium. This you can see on your screens. Now this oxygen picks up a proton and we get a structure in which you can see the resonating structures. When you look at the resonating structures, what you find that in one structure, oxygen has a positive charge on it, and in the second structure, carbon has a positive charge on it. So what happens in the second step? In the second step, a base picks up a proton from the alpha carbon. Why is it so? Because oxygen, since oxygen has a positive charge, it pulls the electrons towards itself, as a result of which the carbonyl oxygen has a positive charge. So this oxygen now pulls the bonds towards itself through inductive effect, as a result of which the bond between the alpha carbon and alpha hydrogen weakens, and now base picks up a proton from here and we get a enol form here. That is, this bond, that is the bond which is indicated with a carbon and the hydrogen, will collapse and make a bond between the two carbon atoms here, and a bond will go on to the hydrogen will go on to oxygen. So this is how we say that the reaction takes place in acidic medium. So let me quickly revise it. In the first step, the lone pair of electrons on oxygen pick up a proton from an acid and we get a structure in which oxygen has a positive charge on it. And in the resonating structure, the second structure that we can see, carbon has a positive charge. So now this positively charged carbon pulls the electrons from the alpha carbon, and this alpha carbon and the bond between the alpha carbon and the alpha hydrogen is weak. So the base in the reaction medium picks up this proton, and this sigma electrons make a bond between these two carbons, resulting in the enol tautomer. Now the second reaction can be carried out in basic conditions. So in basic conditions, you have to remember the reaction is initiated by a base. So what does this base do? It picks up a proton. Which proton? The alpha proton. And when it picks up a alpha proton, what do we get? We get a enolate ion. And this enolate ion is stabilized by two resonating structures. As you can see, the negative charge on carbon results in a bond formation, double bond, between this carbon, the alpha carbon, and the carbonyl carbon. And the oxygen pulls the electrons towards itself and it has a negative charge. Now in the second step, this oxygen picks up a proton from the solvent and is converted into enol tautomer, and the base is regenerated. So this is how the tautomerism or tautomerization can take place in acidic and basic conditions. So now, in other words, we can say when two structural isomers are mutually interconvertible and exist in dynamic equilibrium, they are called as tautomers. In this system, hydrogen atom generally oscillates between three polyvalent atoms. That is, it involves 1,3 migration of hydrogen atom from one polyvalent atom to the other polyvalent atom in the molecule. So what happens is, hydrogen, which is monovalent in nature, it migrates from first carbon to the first atom to the third atom. And the most important, this type of system is known as the triad system. And the most important type of triad system is the keto-enol tautomerism. And the two groups of tautomers are known as keto form and the enol form. I have shown the interconversion of keto and enol form by taking an example of acetone. So when I said it is two things that you have to keep in mind. First is, that is, a hydrogen is migrating from first carbon to a third atom. That is, hydrogen is migrating from the first carbonyl to the third carbon. That is, it is migrating to oxygen. One point. And the second thing that I said was that it is a monovalent atom. So what is the monovalent atom here? It is hydrogen, and it is migrating from first atom to third atom, which is oxygen, as you can see on your screens. So what happens? This bond migrates from here to there. So then we get a double bond here. Oxygen, being more electronegative, will pull the electrons towards itself. So oxygen has a negative charge. And now this hydrogen, it goes on to this oxygen to form the enol form. Here you can see again on your screens that the keto form is nearly 100%. That means the keto form of acetone is more stable as compared to the enol form, and it is the enol form which is known as the labile form. So here again you can see on your screens the keto-enol tautomerism. In keto-enol tautomerism, it is the alpha hydrogen which is indicated by green, which migrates to oxygen, that is first, second and 3, so it is 1,3 system, and we get, and what does it result into? It results into a double bond between two carbons, and the OH group is attached to the carbons which are containing the double bond. So what is the keto group here? You have to remember that how do these two forms differ? The keto and the enol form. As you can see on your screens, in keto form, the functional group is CO, that is, it is the carbonyl group. Here the double bond is between carbon and oxygen. Whereas when we consider the enol form, in enol form we have a double bond in alkene and OH is attached to the carbon which has the double bond. So this form, so that means we are now joining two terms, E and ol. That means that becomes enol. That is, you have to keep in mind that what is so particular about enol. In enol, the OH is attached to a carbon which is containing the double bond. It is directly attached to double bond. If this OH was not attached to double bond, if it was attached to some other position, then it would not be enolic form. Enolic, you have to remember, OH is attached to a carbon which is containing a double bond. That means in enol, the functional group is double bond and a OH. Which OH? Which is attached to this double bond. And in keto form, the double bond is between carbon and oxygen. So this phenomena of rapid interconversion of constitutional isomers is called tautomerism. The term tautomerism is derived from Greek word tauto, means same, meros means parts, was first used by Lahr in 1885. It describes the phenomena of substance reacting chemically according to two possible structures. So when we discuss acetone, what we find that since in acetone 100% or more than 99.99% we have the keto form, it will show more properties of ketonic form. And what we mean by saying it is a dynamic equilibrium. Supposing we are adding a reagent which acts only with the ketonic form, that is, we are adding 2,4-diphenyl hydrazine to the reaction mixture. Then the whole of the mixture will behave as though it is made up of keto form. Because when little amount of keto form reacts with 2,4-diphenyl hydrazine, the equilibrium is disturbed. And more of the enol form will be converted into keto form. So the entire system will behave as though it is made up of keto form. And if we take another example, let's say I am taking an example of phenol. Phenol is also shows keto-enol tautomerism, and in phenol the enol form is more stable. There when we add FeCl3, neutral FeCl3 to it, the whole of the mixture or the whole of the molecule behaves as though it is only made up of enol form. So this is what we mean by saying that they are tautomers and there is a dynamic equilibrium. So now different tautomerism exist depending upon the functional groups present in them. But we shall be in my future lectures, be concentrating on keto-enol tautomerism, which is also known as desmotropism or dynamic isomerism. For this lecture, I had consulted the books by McMurray Jones, Phenol, Morrison and Boyd, and you can also refer to them. Thank you.